So this section of the topic is about saponification. It's the industrial chemistry option, section E, and saponification is a really important process for organic chemistry. And in industry it's used to make detergents, soaps, hand soaps, shampoos, etc. Saponification is the conversion in a basic solution, so sodium hydroxide, of fats and oils to glycerol and salts of fatty acids. And that's the main reaction is in soap making. It's saponification. If we look at what is a fat, what is an oil, they're basically large esters. And they're special esters. They're formed from alcohol. In fact, 1,2,3 propan-triol. So it's propanol with 3 alcohol groups attached. And that's commonly known as glycerol. And that's a long chain alkanoic acid, fatty acids. And this is an example of it here. 3 fatty acid chains, and they're held together with a glycerol molecule. So here's your glycerol molecule, here's your fatty acid chains, and you can see the acid group attached, the COOH, and that's held together by this glycerol molecule. You've probably done these in biology, and you've seen that these fatty acids. Now the reaction used to make soap from these fats and oils is called saponification. And here's the general equation. We have glycerol plus an alkanoic acid, and that gives us fats or oils, glycerides, and water. And this is esterification. If you remember, we had an alkanol and an alkanoic acid, and that formed our ester, and water was produced with it. It was eliminated from the molecule. And remember, we used concentrated sulfuric acid to do that. An example here, we have palmitic acid, and that's attached. So here was the example of your acid. Here, our acid, adding to glycerol, and we get glycerol tripalmitate. So we have our glycerol molecule, and we have 3 of these palmitic acid groups with the and our glycerol groups here. Now the opposite to making an ester is acid hydrolysis, and that's this equation here. An ester reacts with water to produce alkanoic acid and an alkanol. So it's going in reverse, and it needs a catalyst to do that, to force it to go backwards, an acid catalyst. And here's the equation. You can see here's our ester. We've got our alkanoic acid group and our alcohol group that made our ester, and when we use water and a catalyst, we get our original alcohol that came from this part of the molecule, and we get our alkanol. So here we have our ester plus water plus our catalyst, and we get our original alkanoic acid, which in this case is methanoic acid, and our alcohol, in this case it's ethanol. So instead of going this way, back to form an ester, we're doing the reverse, and that's called acid hydrolysis, because we're using an acid to add water, hydrolyze the ester. And our products are alkanoic acid and alkanol. If you hydrolyze using a base, so base hydrolysis is called saponification. It's a reaction of an ester with a really strong base, and it produces the salt of an alkanoic acid. So not the COOH molecule, but a salt of it. And here you'll see the reaction. We have our ester, our alkanoic acid group, in this case 2 C's, so it's ethanoic acid, and our original alcohol, 1, 2, is ethanol. Now if we add this ester to sodium hydroxide, or a basic solution, it produces the alkanoic acid minus the hydrogen, and it receives a sodium, so it makes a salt of an alkanoic acid, not a pure alkanoic acid. It also produces our alkanol. In this case there's a problem here that needs to be fixed, but you can see that's ethanol, and here we've got methanol. So when this ester or fat or oil is hydrolyzed by alkalis, such as sodium hydroxide, soap is formed, and soap is the saponification reaction. Soap is the production of a salt of a fatty acid. So fats and oils, concentrated sodium hydroxide, we get a soap, and glycerol. The glycerol breaks off that molecule that formed the fats with the 3 fatty acids. And that's an example. And this is a full one we see here. We've got our glycerol group, and we've got our alkanoic acid attached. This makes glycerols plus fatty acids. So it's a fat or an oil. We add sodium hydroxide to it. And we add 3 of those because we want to break these bonds here, and we need a sodium for each one of these parts of the molecule. So here you can see we've broken this off. We get glycerol, and we get the 3 parts here, 3, and we get sodium attached. So this part form a negative ion, this part a negative ion, and we attach sodium to it to neutralize this molecule. It becomes neutral. The naturally occurring fat above is glycerol tripalmitate. When it's heated with a base such as sodium hydroxide, the conversion occurs, forming glycerol and a salt that is soap. So it's sodium palmitate. It loses the tri because there's no longer 3. It's separate into 1 group of each. There's 3 of them. Saponification reaction is the reverse of esters, esterification. Except that the water part has been replaced with sodium hydroxide. So we call it alkaline hydrolysis. Now you can't just say whenever you see this word saponification is soap making. You're not going to get a full mark for that. You need to choose one of these definitions, such as saponification is a process by which triglycerides, fats or oils, are reacted with sodium or potassium hydroxide to produce glycerol and a fatty acid salt. This is a salt that's produced by breaking glycerol off, and this is called a soap. Another one is saponification is the alkaline hydrolysis, so using an alcohol to hydrolyze the ester. It produces fatty acid. Sorry, it produces salts of fatty acid. The third one, saponification, is the conversion in a basic solution of fats and oils to produce glycerol and a salt of a fatty acid. This is one way of making soap. So you're putting this sentence before saying making soap. Fat or oil, concentrated sodium hydroxide gives you glycerol and the salt of a fatty acid. Fat or oil and concentrated potassium hydroxide, and it gives you glycerol and potassium salt of a fatty acid. So you've got these two separate ones. Two different equations, both are saponification. Always remember, you get the fat of the oil plus concentrated sodium hydroxide, you get a glycerol and the salt of the fatty acids. They were attached to the glycerol. Just go back to the initial picture here. So here you can see this was our fat or our oil. There's 3 fatty acids. C double O. When you remove this part, it leaves a minus. Makes this whole section a minus ion. That minus ion, one minus, can then attach to a sodium or a potassium positive ion to produce the salt of a fatty acid. In this case, it's a triglyceride. There are 3 fatty acids attached to glycerol. Describe the conditions under which saponification can be formed in the school laboratory and compare these with industrial preparation of soap. And we're comparing, which is similarities and differences, not just similarities. Okay, both. Contrasting would be differences. So making soap in the school laboratory. There'll be video attached shortly in YouTube of this, and you get 50 mils of sodium hydroxide, so it's quite concentrated, and we put that in a beaker, and it's caustic soda, so this stuff can burn you. It's very strong. It's quite dangerous. So we're going to use protective clothing, gloves, and because we're going to be heating this, gloves, safety glasses have to be worn. Now we want to add a fat to this. So we're going to add, before we add our fat we need boiling chips, otherwise you can get bumping occurring. So bumping is when the beaker, the oil in the beaker or the water in the beaker boils at the bottom, and the steam can push the contents of the beaker up and even out of the beaker. So we need boiling chips to get the distribution of heat evenly throughout the solution, and to give a nucleus for small bubbles in case it gets that hot. And the nucleus for bubbles means the bubbles come from the stone chips, not the whole bottom of the beaker, and cause bumping. And we need our fat, which is castor oil. We're going to use olive oil for our example. Heat the mixture gently on a hot plate for about 20 minutes. So that's our sodium hydroxide and our oil. We then add some water to keep the volume of the mixture constant. So if we're heating a concentrated sodium hydroxide solution, we're losing water continually. We need the concentration to stay at about 5 moles, not become stronger as we lose water. It leaves the sodium hydroxide behind. So we're going to add water a little bit at a time so it doesn't cool down too much, and so the level of the water stays the same. When you can no longer see the fat, that means it's reacting with the sodium hydroxide. It's being spread throughout the solution. That's when we allow the mixture to cool down, and we're going to stir in our sodium chloride, a brine solution, and then we're going to heat the whole mixture. After it's cooled down, we're going to heat it up for 3 minutes, and we allow it to cool, and we break up the solid pieces so a solid scum will form. That's the salt of a fatty acid. And we add this sodium source here, our saturated sodium chloride solution. It reacts with all of the ions from the fat that have been separated from the glycerol molecule. Break up the solid pieces with the spatula. We pour off the liquid and wash the solid mass with water to get rid of any sodium hydroxide or sodium chloride. We want to make sure if we're going to test this soap with our hands, and we're going to use gloves, we don't have any of that sodium hydroxide, concentrated sodium hydroxide there. So here you can see the reaction. We have steam forming that's escaping, so we need to add some water. The watch glass just prevents too much water from evaporating. Our oil, we're going to use olive oil. We have our soap. This is the curd that forms on the top when you add the sodium hydroxide solution. So this is our soap. This is the remainder. Castor oil, just an ester. Our fats and oils are esters, types of esters. Remember, fatty acid attached to glycerol molecule. We then test the soap. So we're going to test it, collect that soap layer, wash it, add 2 ml of distilled water to our test tube, add a spatula of the soap and shake. Now, assuming the water isn't hard, we're going to get our lather produced, which is our bubbly, frothy mixture. If the lather produced is quite good, then our soap is good quality. We're going to add 2 ml of water to another test tube, and this time, so one we're going to add the soap that we made. The second test tube we're going to add some vegetable oil. Now, if you see that second test tube has oil in it, the oil turns into globules, sort of sticks together, it doesn't mix very well. We're going to add soap to that mixture, and when we shake it, the oil will break up, and we call that an emulsion, and the soap is acted as a surfactant, and we'll see that later, what that means. So why did we add the sodium chloride solution? The soap produced can be precipitated by adding concentrated sodium chloride and then washed to remove that glycerol and extra sodium hydroxide. Dilute hydrochloric acid could also be used to neutralize the excess sodium hydroxide. If we looked at this, typical neutralization reaction. And that's to get rid of this excess sodium hydroxide. You need the same amount, or be able to work out when it's neutralized, all of it, with an indicator. Okay, so our soap's produced by precipitating that salt of the sodium with our fatty acid. in industrial production of of soap, so industrial saponification is pretty much the same as in the laboratory. The hydrolysis process, where fats molecules are broken down to produce glycerol and soap. The fat and oil feedstock. So this is the supply of fat and oil that's put into the process, is mixed with concentrated sodium hydroxide. And that happens in large vats called like kettles, if you think of a kettle for boiling water, but on a much bigger scale. And we have the sodium hydroxide and the fat and oil put in there. Large scale, remember. We have steam that blows into there to heat up the mixture. In the laboratory we use basically a heater to do it. The soap is separated from the reaction mixture. It's washed with hot brine that dissolves any glycerol that we have, and it leaves behind the insoluble soap. It's called salting out. So this insoluble soap, is what we have precipitated out. The mixture separates into two layers. The soap curd overlays the lye layer. This lye layer contains brine, glycerol and some alkali. And lye, it's a term they use in America for that alkalized salt mixture. This lower layer is pumped out and the valuable glycerol is extracted, so we keep that and we can use that again. Brine is returned to the kettles and that can be reused. And here's the process. So we have a kettle, brine is injected in, oil and caustic soda are injected in, steam is used to heat. And the soap curd is treated with water to remove the excess salt and alkali before vacuum drying it to make flakes or solid dry soap, bars, powders, powder for the washing machine to wash your clothes with. Colours and perfumes could be added. Also we could have UV reflective materials to make things look whiter when they're washed. And then it's ready for packaging. So there's two processes, the one in the school laboratory and one in the industrial process. And you can see the similarities of those two are both have fats and oils. It's our triglycerides. They're both mixed with concentrated alkali and they're both heated, one with steam, one with a laboratory heating pad. Concentrated brine is used to separate the soap from the aqueous phase, so to get the soap out of the water. Aqueous, water. Crude soap that we have forms a layer and it's washed, and then it can be dried and treated later. Okay, in the laboratory we'd wash it, dry it off, be careful, and then test our soap. The differences between those conditions, so the lab and the industrial production of soap. Let's see here, the raw materials. So in the school we used castor oil or olive oil, sodium hydroxide. We didn't control these amounts precisely, we just did it to get a result. So sodium chloride is used to make that precipitate, to make the soap come out of the solution. And we don't really use hydrochloric acid to neutralize any extra sodium hydroxide. In industry, and things on a much larger scale, they have a variety of blended oils with sodium hydroxide. They extract the proper proportions that the exact proportions are used. They don't want waste materials, they don't want extra product, they don't want extra one of the reactants. So they need the exact right amount. Remember, they're doing this for yield and for minimal expense. Sodium hydroxide is used to precipitate the soap, so the same as in the school example. However, they use acid to neutralise any excess sodium hydroxide. The raw materials, they're all mixed together at the start. In the kettle method, they hydrolyse the fats and oils, and then they use neutralisation to get rid of any extra sodium hydroxide. Time, this can be done in one day, including drying time, heating and cooling times. The washing and settling of soaps can take several days in an industrial process. For the temperature and pressure that we want, a hot plate is used, a hot plate. We don't really use pressure in the school laboratory. It's too expensive, difficult to do any adjustments or to perform the reactions if you can't reach them if they're in a container. In the industrial process, we have hotter temperatures used in the kettle and higher pressure used. The container, we can do it in a beaker in the school laboratory. In the industrial process, large kettle producing bulk amounts, so lots and lots of it, so it's about bulk. It means large amounts of our products. In the school laboratory, they don't use a catalyst. We didn't use a catalyst. In the industrial process, a metal catalyst can be used. Stirring, we use that manual glass stirring rod, but they use steam to power and heat, or electrical energy to stir in the industrial process. Safety precautions, so we wear goggles, gloves, safety equipment, protective clothing. We heat gently and stir constantly to avoid any spitting or bubbling of the sodium hydroxide. If it gets on your skin or in your eyes, it can cause major damage, cause burns. In the industrial process, they've got high pressure, which means that extra care needs to be taken. Goggles, protective clothing has to be worn in the plant, but because of that pressure, high pressure sodium hydroxide could be sprayed out and cause major damage, loss of life or injury. Further processing, we wash it to remove any extra sodium hydroxide. We can add things to it, perfume, and we can dry it. In the industrial process, they wash it with steam, add dyes and perfumes, and they can even distill the soap. So melt it down to remove any impurities. Then it can be vacuum dried. That's drawing all the moisture out of it. Okay, that's the end of that section. We'll be back later with another section. So here was the example of your acid. Here, our acid, adding to glycerol, and we get glycerol tripalmitate. So we have our glycerol molecule, and we have 3 of these palmitic acid groups with the and our glycerol groups here.